Welcome back everyone to exploring how to actually perform random forests for classification. In part 2, we're going to work with a more realistic example, working with a grid search and cross-validation with a random forest. So we'll begin to explore a larger data set, and it's going to be the popular banknote authentication dataset from the UC Irvine Machine Learning Data Repository. This is known as the banknote authentication dataset, and essentially real and fake bills are image scanned, and then a wavelet transformation was performed on the image, allowing us to get numeric properties from the actual image of either the real bill or the counterfeit fake bill. And so the features are variants of that wavelet transformation, the skewness and kurtosis of the wavelet transformation, as well as the entropy of the image, essentially a measure of how much noise there was in that image. With these four features, let's go ahead and explore hyperparameters in a random forest for classification. I'm going to head over to the notebook. Okay, here I am at the notebook. I'm going to be reading in the file, so we'll say pd.readcsv, and underneath the data folder, there is a file called /data banknote authentication.csv. So you should be able to tab autocomplete that, and then we're going to hit enter here. If we check out the head of this data frame, notice we have the four features I mentioned off that variance, skewness, and kurtosis of the wavelet transformation, as well as the image entropy, how much noise there was in the image, and the class. So we have a class 0 or 1 indicating whether or not it is a counterfeit bill or a true bill. And then we can do a simple visualization of the data with a pair plot. So I can just pass in the entire data frame and then set hue equal to class. And you can check out the corresponding lecture notebook for the link to the official documentation on this dataset from the UC Irvine Machine Learning Repository. If we just do a simple pair plot, this will allow us to actually do a scatter plot colored by the hue. And the thing that should really jump out to you is the fact that these are actually quite easily separated. You'll notice there's clear distinctions between the distributions of class 0 and class 1, the real bills versus the counterfeit bills. And for some feature combinations, like kurtosis wavelet and image entropy, they seem to be quite similar to each other, but for many of these features, it looks like there's going to be clear separation, which means if we're able to use combinations of these features, we should be able to get pretty good accuracy of the classification. Let's move on to actually building out our features and label. The features are simply going to be df drop class along axis is equal to 1. And recall, when it comes to tree-based methods like a single decision tree or a random forest, I do not need to worry about having to scale or standardize or normalize any of these feature data points, since we're just going to be doing a split based off a single feature. So it's just going to ask you, based off that feature, is it more than or less than any particular value? Which means I don't need to normalize that or standardize it in terms of the rest of the features, which is quite nice. So we can essentially skip that step for these tree methods. So I'm going to say X, my features are all the columns except the class column, and my Y label is df class. Now let's go ahead and do the train test split. We say from scikit-learn model selection, import a train test split, and then we say train test split. Go ahead and grab the tuple unpacking code. So at the bottom we have that example. Let's go ahead and grab it. Let me paste that back in here. And then what I'm going to do is I'm going to set the test size to be a little smaller since we're going to be performing cross-validation. This is essentially a holdout test set. We will be using grid search CV. So I'll say the test size is 15, and let's use a random state of 101. Obviously this is something you can change, but just for replication purposes, you can follow along with me here. So this is going to be our holdout test. X test and Y test will be holdouts, because we're going to perform a grid search. So we'll say from scikit-learn.model selection again, import grid search CV. So we're going to perform cross-validation and a grid search to figure out what are the best parameters. And recall, for a grid search CV, we need to set up a parameter grid, which means I should understand what I can actually play around with for my random forest classifier. Let's go ahead and import the random forest classifier. We say from scikit-learn, and remember it's from the ensemble family of models, import random forest classifier, and then you can call help on random forest classifier. to get an idea of the various parameters you can begin to edit. So we have number of estimators, we have all the tree-based parameters that we could edit. We haven't really been focusing on that, but that is something you can begin to explore. And the most important ones that we really want to focus on are really how many estimators do we need to worry about here. And then what we can also do is check out the max features to use. So in total, if we come back up here, there are really only 4 features to consider. So what we could do is just make a list of considering 2 features at the split and then get one of those, or 3 features randomly chosen, or all 4 features randomly chosen. Recall that the way random forest works is every time you're coming up to a split, I'm going to grab a random subset of those features. So I could grab 2 random features, 3 random features, or check out all 4. Scroll back down here. In order to set this up, we need to begin to set up the parameter grid. So let's play around with estimators. We'll say number of estimators. I'm going to set this equal to 64, 100, 128, and maybe a large value like 200. So I'm just going to make some values to fit into my parameter grid dictionary. Then for max features, I can do something like a list of strings, auto, square root, log 2, or for a smaller set of features, I can manually define them. Choose 2 random subsets, or 3, or 4. 4 would just be all the features considered. So let's go ahead and do that. And then for Bootstrap, if you want, you can check out the differences between bootstrapping the data or not bootstrapping the data. So I could have bootstrap is true or false. The next hyperparameter that I want to explore is out-of-bag score. Recall from our theory and intuition lectures, out-of-bag score is not really a hyperparameter that we pass in that is going to affect the training of the model. It's essentially going to tell the model, in the instances where bootstrap happens to be true, go ahead and also calculate that out-of-bag score. That is, the rows that were not used during the bootstrap sampling for certain trees. It's definitely not a replacement for something like accuracy, precision, and recall, but it is more information about how a group of decision trees within your random forest happen to perform on data that it did not see. So because it's essentially kind of free information or free performance metrics, we're going to go ahead and say true, comma, false here. Keep in mind that as we run our grid search of cross-validation, there are going to be errors and warnings. And why is that? Well, out-of-bag score is only possible when bootstrap is equal to true, which means in the instances where we have a combination of bootstrap equal to false, that means we're not actually going to be able to have out-of-bag score equal to true. So it's going to happen in the instances where bootstrap is equal to false and out-of-bag score is equal to true, the fit will just fail and it will warn you that it's impossible to calculate out-of-bag score if you did not perform bootstrapping to begin with. So keep that in mind. As you see the grid being fitted, you will get some warnings essentially telling you the fit failed. That is to be expected given the way we're organizing it here. So now let's set up our parameter grid dictionary. We say param grid, and then I just pass in an estimators. As always, these string key names have to match up with what random forest classifier expects, which is why I just recommend keeping the variable name the same as the key name. So we'll say nestimators, then the key max features. Then we're going to have bootstrap, and then finally out-of-bag score, and OOB score. Okay, so we have our parameter grid set up. Let's go ahead and say RFC is equal to an instance of a random forest classifier. And just in case you haven't imported it yet, remember it's from scikit-learn.ensemble, import random forest classifier. So we're going to set up our base model, and now we're going to set up our grid. So the grid is just the instance of grid search CV. So we say grid is equal to grid search CV, but in this case, I pass in my base model, and then I pass in the parameter grid that I wish to explore. And just like a normal model, we fit it to our training data. So we say fit on X train and Y train, and then let this run and fit. Again, it's going to start off with no complaints, but eventually we should get to the point where we are saying bootstrap is equal to false, but we're trying to combine it with out of bag score is equal to true. In which case, we should get a bunch of warnings eventually on this fit command that a lot of the remaining fits ended up failing because out of bag score is essentially not possible or only available if bootstrap is equal to true. And there we can begin to see the warnings right here. So if you see it, don't worry about it, just read it and understand it. So we say value error, out of bag estimation, only available if bootstrap equal to true, which makes sense, so the estimator fit failed. No worries, that wasn't really a fit that we're interested in because we have the backup fit for when bootstrap is false, there's going to be an instance where out of bag score is false. Okay, now with that being said, we're going to move on here to check out the best parameters. So we say grid dot best params, we can also say best estimator, run that, and it looks like the best parameters does involve bootstrapping, and then we say max features is 2, and estimators is 200, and notice here, this is kind of the trick with grid search. It happened to say out of bag score is false, but we do know that we could have had a model where out of bag score was true. And because out of bag score isn't really a hyperparameter that affects training, this is going to be a kind of tricky part you have to keep in mind when you're fitting to your random forest. So just by chance, it happened to fit bootstrap true with out of bag score false first with max features 2 and estimators 200, which means if I do want that out of bag score, I should probably just create that individual model myself. So we're going to say RFC is equal to random forest classifier, and then I'm going to pass in, well, we already know bootstrap is true by default, so I'm just going to pass in max features is equal to 2 and estimators is equal to 200. And the reason I'm kind of redoing this again is to make sure that out of bag score is equal to true, since by default it's false, which is why it's leaning here to false. And as I keep mentioning, out of bag score isn't really something that affects the training. It's just something that says, hey, I would also like to keep track of this particular performance metric since bootstrapping is true. So now let's create that model. Say RFC fit to xtrain and ytrain. Run that, and we have our model where we can now perform predictions off of and get some performance metrics. So we're going to say RFC, and after you fit the model, you should be able to see out of bag score. And there's two, out of bag score and out of bag score with an underscore after it. If you just say OOB score, it's going to report back whether or not you said true or false during training. To get the actual score value after training, say OOB score underscore. And then it's going to tell you how well it performed there. You notice we're almost getting a perfect out of bag score, which would be 1. So we're performing quite well there. Essentially, the percentage of the classifications that are correct in this particular case. So let's get some predictions and compare this to the classification report. So we're going to say grid.predict. Actually, not grid. We're going to say RFC.predict. I'm going to pass in xtest. And then I'm going to import, or say from scikit-learn.metrics import. Let's go ahead and import the plot confusion matrix, and let's import the classification report. So let's print the classification report, which is going to compare our yTrue, which is yTest, to the predictions. Here we go, and notice we should get pretty similar results on things like accuracy to what you see on out of bag score. These two numbers here shouldn't be wildly different. Keep in mind they are different numbers. This is running it across the entire random forest, so every single decision tree. And out of bag scores is kind of a culmination of different sets of decision trees. So keep that in mind, and again, review the out of bag score and bootstrapping lecture in case that's confusing to you. This is kind of just think of it as a bonus performance metric you can check out, although usually it's going to be quite similar to your overall accuracy. Now what we can also do is see how many we actually misclassified by doing something like plot confusion matrix. So plot confusion matrix, and then we can say RFC xtest ytest, run that, and we can see here it looks like we only misclassified 2 of those data points, or 2 bills. Now, another thing to note is this particular data set did not have too many features. So something that would be interesting to explore is to see if we even really needed these 200 estimators. What we could do is, based off using max features of 2, we could begin to explore and plot out error versus number of estimators and see where it begins to level off, whether we needed 200 or if it just happened to be that way for this particular matchup of the various parameters. So what we could do is scroll down here and set up a little loop for the following. We could say errors and then misclassifications as 2 empty lists, and we're going to say for n in range, we can go from 1 to 200 estimators. We're going to do the following. We'll create a new estimator. We'll say random forest classifier. So we'll simply say random forest classifier. We'll say number of estimators is equal to n. So we're going to create a classifier for n is equal to 1, 2, 3, 4, and so on. And keep in mind, this could take a while depending on how large of an n you choose. And we'll also say max features is equal to 2. Although that's technically equal to the square root of 4. So it's very similar to the default value. And then what we're going to do here is say RFC fit to xtrain and ytrain. And let's get the predictions. We'll say preds is equal to RFC dot predict off x test. And let's calculate our error. So one way to calculate error is through an accuracy score. So I could actually, up here, instead of just importing plot confusion matrix and plot or classification report, I can also import accuracy score. So run that. Recall we have this accuracy score. So after doing that, I can get my error by saying it's equal to 1 minus the accuracy score, which simply takes in y true versus y pred, which in our case would be y test versus my predictions. So accuracy score would be 99% accurate, for example. So if we say 1 minus that, then our error is 1%. So that's why I'm doing the 1 minus accuracy score for what I'm calculating as error. I could also just keep in track of how many misclassifications I'm actually getting. So I could do that by saying n missed is equal to np sum of predictions that don't match up to y test. Now let me take a little bit of time to explain this one line because it's often confusing to beginners who haven't seen this sort of calculation before. What I'm going to do is come back up here, recall that we have our predicted values, that is the predictions, and then y test. And what we're going to do is in this line, I'm going to compare where they actually match up. So let me show you that in a cell above. So recall we have our predictions, which is a bunch of zeros and ones, and then I also have my y test value, which is again essentially a bunch of zeros and ones. So if I ask where's y test not equal to predictions, I should get a bunch of Boolean values, falses, and somewhere along the line, hopefully there was a match. So for example, if I said equals equals, that would be the actual matches. But I'm looking for misclassifications. So the instances where y test didn't match up with predictions. So where there was a 0 in the predictions and there was a 1. So because these are all false, that means that actually was a match. So if we explore again y test, notice the very first one is 0, and so is the prediction. So that's a correct match. And we're looking for misclassifications, of which there were only 2, so we'd expect a bunch of falses here. So if I say, where's y test not equal to predictions, I get back this series of Booleans. And Booleans can be treated as zeros and ones when you actually sum them up. So then I could say np dot sum of this, and it's going to report back 2. It just reports back how many trues you had. So that means there were 2 instances where y test did not match up with predictions, which is exactly the same result we have up here. So this is just one way of calculating your missed or misclassifications. So once I have the error and misclassifications, I'm just going to take my errors and append them. And I will do the same thing for misclassifications and append those and missed. There we go. And so while this is running, what I can do is begin to set up the plot. So I would like to plot my error versus the number of estimators. Same for my misclassifications versus the number of estimators. And if this takes too long, you can always make this a much smaller number. You should see it die off quite quickly. In fact, it only takes about 10 estimators in this particular case to start getting good performance. So what I'm going to do here is say plt.plot, and I'll plot range from 1 to 200 versus my errors. And then I will also plot, plt plot, forget that parentheses there. There we go. So plt plot 1 versus 200 of my errors. And you'll notice we start off with quite a bit of noise in the errors, and eventually we start to settle off and we start to hit this, essentially, this point or threshold where I can no longer really improve performance, which is exactly the same thing we discussed in the theory and intuition lectures, that eventually adding more trees is not really going to help you. And in fact, if we take this plt.plot, and again I plot range 1 to 200, but this time versus the misclassifications, you'll notice that at the beginning I'm performing almost like 4 or 5 misclassifications, but I start, no matter how many trees I begin to add in, I'm basically just hitting either 1 or 2 classifications. So sometimes for a certain number of trees I get a little lucky and I hit 1 misclassification, but mostly it seems like we're starting to level off at 2 misclassifications, which is quite interesting because, as Leo Breiman said, they don't overfit. What's going to happen is just going to reach this threshold limit of performance. So what this means, 200 was probably way too many trees, and we could have just shortened it down to somewhere around maybe the 25 mark. You can see between 25 and 50, you're really just getting either 1, 2, or 3 misclassifications. So kind of interesting to plot this out in order to explore how many trees are really necessary. Okay, that's it for this lecture series. Coming up next, we're going to talk about using random forests for a regression task, that is, a continuous label. I'll see you there.